Dear students, we will start with Module 4 of Control Systems, Stability Analysis. First, there are two important concepts which need to be discussed with respect to the stability analysis. The first one is Routh stability criteria. This is one major unit. The second one is root locus. This is the second half of this module. So first let us start with Routh stability criteria. So first let us know what is the definition of stability analysis. The analysis of whether the given system can reach a steady state passing through transients successfully is called stability analysis of the system. So this is the definition of stability analysis, and we will classify the system is stable, unstable or marginally stable based on certain condition. Okay. So that is, we will consider characteristic equation of a closed loop control system, and we will classify it as unstable. So if any one of these two conditions are satisfied. First is, if the roots of the closed loop poles are present on the right hand side of S plane. If you take S plane, so if any roots, if it is present on the right half of S plane, so it will tell that the system is unstable. The second one is, if the roots of the closed loop poles are present on the imaginary axis and if they are repeated. Okay. So what is the meaning of repeated? So if there are two poles which are present at plus 2j or minus 2j, so the roots should be repeated. Okay. If there are two roots which are present at plus 2j and plus 3j, they are not said to be repeated. Only if they are present on the imaginary axis, and if they are repeated, they are said to be, and the system is said to be unstable. So when the system is said to be stable, if the roots of the closed loop poles are present on the left hand side of S plane, then we will say that the system is said to be stable. Okay. Third one, marginally stable. If the roots of the closed loop poles are present on the imaginary axis and not repeated. Okay. So in the third condition, marginally stable, so in the first case unstable, the second criteria was if they are repeated on the imaginary axis, the system is said to be unstable. So when it is said to be marginally stable, okay, so it is neither fully stable nor unstable. It is marginally stable. It is in between stable and unstable. Okay. Under which condition? If the roots of the closed loop poles are present on the imaginary axis and not repeated. So what is the meaning of not repeated? So if there are two roots, okay, so one of the pole is present at plus 3j, the other one is present at plus 2j. Okay. These two are different. Okay. So if the roots are different on the imaginary axis, that is, they are not repeated, then the system is said to be marginally stable. So here we have said that based on the characteristic equation, okay, we will obtain the closed loop poles. Okay. So what is the meaning of open loop poles? If we equate the numerator of g of s into h of s equal to 0, we will get open loop poles. Closed loop poles are, the characteristic equation is obtained by taking the numerator of 1 plus g of s into h of s equal to 0. So this is very important. Okay. So in some of the problems, only g of s into h of s will be given. You have to convert it into closed loop poles by writing it as 1 plus g of s into h of s equal to 0. So, and you have to take only the numerator. Okay. So we will obtain the characteristic equation. Okay. So this is just about the introduction. when will we say that the system is unstable, stable and marginally stable? So next we shall move on to the major important concept of this model, Routh stability criteria. So Routh stability criteria, so here, okay, so Routh stability criteria, it is also called as Routh Hourwitz criteria. Okay, so the general characteristic equation f of s, if it is written as a naught into s power n plus a1 into s power n minus 1 plus a2 into s power n minus 2, so on till an into s power 0. S power 0 is value is equal to 1, so it's not written. Okay, it's equal to 0. What you can observe here, we are written the equation according to the decreasing order of s power. Okay. So first we are written s power n minus 1, s power n minus 2, s power n minus 3, so on till s power 0. And what is a0, a1, a2? They are the quotient of s. Okay, so a0 is the quotient of s power n, a1 is quotient of s power n plus s minus, sorry, a1 is the quotient of s power n minus 1 and a2 is the quotient of s power n minus 2, so on. An is the quotient of s power 0. So what is the procedure to write the Routh array? So first you have to take the highest power of s in the first row. So what is the highest power of s? S power n. Okay. So next in the second row you have to take the next highest power. Next highest power of s is s power n minus 1. Okay. So in the first row what we will do? So s power n. What is the quotient of s power n? a0. Okay. We have written a0. Next, okay, the next n minus 2. Okay. N minus 2 quotient is s power n minus 2 quotient is a2. Okay. Similarly, if you take the next s power n minus 4 quotient, it would be a4. Similarly, the next s power n minus 6 quotient value will be a6. This is about the first row. Okay, so always you have to take my highest power quotient first. Next, take the highest power quotient minus 2. Okay, you'll get a2, then a4, then a6. In the second row, we'll take the next highest power of s. Okay, that is s power n minus 1. Okay, so what is the quotient of s power n minus 1 here? It is a1, then s power n minus 3 quotient. Okay, s power n minus 1 minus 2. It will be s power n minus 3. The quotient of s power n minus 3 would be a3. Similarly, the next lower power of s would be s power n minus 5. S power n minus 5 quotient would be a5. Similarly, s power n minus 5 quotient, s power n minus 7 quotient would be a7. Okay. So this would be clear when we discuss the problems. So only first two rows of the Routh array will obtain from the characteristic equation or the closed loop poles equation. What about the third row? S power n minus 2, s power n minus 3, so on till s power 0. Okay, you have to obtain it by taking the formula. Okay, b1. So b1 is written as, you can see the next step, the negative of the determinant. Okay, so b1. Okay, we will take the first column a0, a1, and the second column a2, a3. The negative of this determinant divided by the second row first element. The second row first element is a1. Okay, so negative of this is equal to negative of the determinant is, so for the positive of the determinant, what we will do? We will take the primary diagonal element minus secondary diagonal element. Okay, so negative of this is written here, b0 equals first, so secondary diagonal element a1 into a2 minus a0 into a3, that is minus primary diagonal element divided by a1. Similarly, Next, if you consider B2, so how is B2 written? For B2, we'll consider the first column. So always for any element, the first column will be the first column A0, A1. Okay. The next second column will be the next column of the previous two rows. Okay. The next column of the previous two rows are, okay, there is, we have to consider the third column. Okay, A4, A5. So negative of minus A0, A1, A4, A5. Okay. So that is, you have to take the secondary diagonal elements minus the product of the primary diagonal elements. Okay. Determinant, how you take that determinant in the same way. A1 into A4 minus A0 into A5 divided by A1. This is B2. Similarly, B3 is given by negative of the determinant of, okay, again the first column elements you have to take as it is A0, A1. So for B3 you have to take the next column. Okay, so that is the fourth column. Fourth column elements are A6 and A7. So negative of this determinant is equal to A1, A6 minus A0, A7 divided by A1. Okay, so in this way we have determined the third row elements B1, B2, B3. Okay. In the same way you have to find the next row elements C1, C2, C3. Okay, that is the power, okay, S power n minus 3 elements. So C1 is equal to, so for C1, okay, you have to consider the previous two rows. Okay, what are the previous two rows? Okay, A1, B1. Okay, you have to consider the previous two rows should always be taken. Okay, so for C1 it will be negative of the determinant of A1, B1, A3, B2 divided by B1. Okay, so it is equal to the product of the secondary diagonal elements A3, B1 minus A1, B2 divided by the first element in the previous row. What is the first element in the previous row? B1. Similarly, C2, for C2 we will take it, the reference will be the first column and the third column of the previous row. Okay, so that is A1, B1 and A5, B3. So it will take the product of the secondary diagonal elements A5 into B1 minus A1 into B3 divided by B1. Okay, always you will divide by the first element of the previous row. Similarly, C3 is given by A7 into B1 minus A1 into B4. Here B4 is not written. If B4 is there, you can write B4 also. B4 divided by B1. So you have to continue this process till S power 0 row quotient. Okay, so if you take, what will be the next row? D1, D2, D3. So how will, so for D1, D2, D3, what you have to take? The previous two rows, that is B1, B2, B3, C1, C2, C3 should be taken as a reference. Okay, continue the process till you go for the lowest power of S, that is S power 0. Okay, so how will you determine whether the system is stable, unstable, based on the Routh stability criteria? Okay, the system is said to be stable, okay, when there are no sign changes in the first column of the Routh array. The system is said to be stable. Okay, for the system to be stable, what should happen? In the first column of the Routh array, there should not be any sign changes. Okay, now we will get two possibilities. All the elements in the first column can either be positive, majority of the cases it will be positive, or all the elements in the first column should be negative. Okay, very rarely you'll have all the elements in the first column will be negative. Okay, second case, when the system is said to be unstable. Okay, if there are any sign changes in the first column of the Routh array, the system is said to be unstable. Okay, and how will you say how many poles are said to be on the right hand side of the S plane. And so this is based on the number of sign changes. Okay, if there are two sign changes in the first column of the Routh array, you say that the system is unstable and two closed loop poles are present on the right hand side of S plane. If there are four sign changes, you will say that there are four closed loop poles which are present on the right hand side of the S plane and the system is said to be unstable. Okay. So this is about Routh stability criteria. Okay. This will become much clear when we discuss some problems. Okay. When we discuss the problems, the concept will become much clear. So we'll go with the problems. First we'll solve very simple problems. Then we'll go with complex problems. So problems, first problem, very simple. Examine the stability of the characteristic equation f of s equals s power 3 plus 6s square plus 11s plus 6 equals to 0. So first what we have to do? We have to write the highest power of s. What is the highest power of s? S cube. Then in the second row, we have to write the next highest power of s. What is the next highest power of s? S square. So first element in the first row is what? S cube is the highest power. What is the quotient of s cube? Okay. Nothing is okay, so it's just written as s cube. So by default, if nothing is there, its value is equal to 1. What is the, how will you write the next element? S power 3 minus 2. Okay, so s power 3 minus 2 is 3 minus 2 is 1. So s power 1. What is the s power 1 quotient? It is 11. Okay, so again I'll tell. First you have to write the highest power of s cube. In the second row, then next highest power of s square. So what is the quotient of s cube? It is equal to 1. What is the quotient of the next highest term? S power 3. So 3 minus 2. 3 minus 2 is 1. So s power 1. S power 1 quotient is 11. Okay. So coming to the second row, s square. S square quotient is 6. Okay. So s power 2. Okay. Minus 2. So 2 minus 2 is 0. So you'll get it as s power 0. What is the value of s power 0? S power 0's quotient is here, it is equal to 6. Okay, we will write it as 6. So first two rows we are written according to the characteristic equation. The next row should be written based on the Routh array. Okay, s power 1. So it is written with respect to the first two rows, previous two rows. So that is secondary diagonal elements product, that is 11 into 6 minus 1 into 6 divided by the first element of the previous row. What is the first element of the previous row? It is equal to 6. Okay. So again I'll tell. So the product of the secondary diagonal elements 11 into 6 minus the product of the primary diagonal elements 1 into 6 divided by the first element of the previous row. The first element of the previous row is 6. So if you solve this, 11 into 6 is 66 minus 6 divided by 6. 66 minus 6 is 60 divided by 6 is 10. Okay. So next element, okay, you don't have any element in the third column, so you'll write as 0. So 0 into 6 minus 1 into 6, it will be 0 only. Minus 1 into 0, okay, it will be 0 divided by 6, it will be 0 only. Okay, third column is absent, so you'll write it as 0. So next, coming to the s power 0. So for s power 0, what will take? The previous two rows, that is s power 1 and s power 2 will be taken as a reference. So 6 into 10 secondary diagonal element product minus the primary diagonal element product 6 into 0. So 6 into 10 is 60 minus 6 into 0 is 0. 60 divided by the previous row first element 10. 60 divided by 10 is equal to 6. Okay. So if you observe the values in the first column of the Routh array, they are plus 1 plus 6 plus 10 and plus 6. So what you can comment here, examine the stability for the characteristic equation f of s equals s power 3 plus 6 s square plus 11s plus 6 equals to 0. Okay. So how we can comment on this stability? You can observe that all the elements in the first column are positive. Okay. So what does this indicate? The system is said to be stable. Okay. You can comment that since there are no sign changes in the first column of the Routh array, the system is stable. Okay. Very simple. Okay. Next, second problem. Examine the stability and comment on it for the characteristic equation s power 4 plus 2s cube plus 4s square plus 6s plus 8 equals 0. So what is the highest power of s here? S power 4. The next highest power of s is s cube. Okay. So first row is written as s power 4. The next row is written as s cube. So what are the, how will you write the elements in the first row? So the quotient of s power 4. What is the quotient of s power 4? It is equal to 1. Next, s power 4 minus 2. What is 4 minus 2? It is 2. What is the quotient of s square? That is equal to 4. Similarly, 2 minus 2, it is equal to 0. What is the quotient of s power 0? It is equal to 8. Next, in the second row, s cube quotient is equal to 2 and 3 minus 2 is equal to 1. S power 1 quotient is equal to 6. Okay. So s power 1 minus 2, you'll have s power minus 1. S power minus 1 is not defined here. Okay. So we'll write as 0. So now, how will you write the next rows? The next rows are written based on the Routh stability criteria. Okay, that is, you have to take secondary diagonal elements product minus primary diagonal elements product divided by the previous row first element. Okay, so s square, how it is written? We are taking here the secondary diagonal elements product 4 into 2 minus 6 into 1 divided by 2. So 4 into 2 is what? 8 minus 6 into 1 is equal to 6. 8 minus 6 is equal to 2. 2 divided by 2 is equal to 1. So the first element is equal to 1. Next, go into the next element. Okay. You have to take the first column and the next column. The next column is equal to the third column. Okay. So that is 1, 2 and 8, 0. So first, the secondary diagonal element product 2 into 8 is 16 minus 1 into 0. 16 minus 0 divided by 2. 16 by 2 is equal to 8. Okay. So we have got it as 8. Next, similarly, s power 1. So s power 1, how will you take it? So s power 1, the previous two rows are s cube and s square. So first element is written based on the first column and the second column. So the product of the secondary diagonal element of s square and s cube is 6 into 1 minus the product of the primary diagonal elements. What is the product of primary diagonal element? 2 into 8 minus 2 into 8 divided by the first element of s square, previous row, divided by 1. So 6 into 1 is 6 minus 8 into 2 is 16. 16. So 6 minus 16 is minus 10 divided by 1. Minus 10 divided by 1 is minus 10. Okay. So next element is 0 because you can see s cube and s square, third column values are 0. Okay. Since both the values are 0, you will get s power 1 value will be 0 only. Okay. The second element will be 0. Similarly, going with the next last power of s power 0. So you will take the previous two rows will be taken as reference, s power 1 and s power 2. Okay. So the product of the previous okay, the product of the secondary diagonal elements of the previous two rows. So that is 8 into minus 10 minus the product of the primary diagonal elements. Product of the primary diagonal elements 1 into 0 minus 1 into 0 divided by the first element. The first element is minus 10. Okay. So 8 into minus 10 divided by 1 into 0. It will get us. So 8 into minus 10 is minus 80 divided by minus 10. Okay. Minus 80 divided by minus 10, it is equal to plus 8. So if you observe the values in the first column, okay, it is plus 1, plus 2. Again, the third element in the S square is plus 1. In S, with respect to S power 1, it is minus 10. With respect to S power 0, it is plus 8. Okay. You have to observe only the elements in the first column of Routh array. Okay, you can observe it is plus 1, plus 2, plus 1, minus 10 and plus 8. Okay. How many sign changes are there? The sign changes are indicated by arrows here. Okay. From S square, it is plus 1. In S power 1, it is minus 10. Okay. So here there is, okay, one sign change. Okay. From plus 1 to minus 10. Okay. Again, S power 1 to S power 0, the first element is minus 10. It has changed to plus 8. Minus 10 to plus 8. Again, there is one more sign change. Okay. There are two sign changes in the first column of Routh array. So it is said to be, so the system, will say that the system is said to be unstable, and we'll say that two closed loop poles are said to be present on the right hand side of S plane. Two closed loop poles are said to be present on the right hand side of the S plane. So the system is said to be unstable. What is the reason? The reason is that there are sign changes in the first column of the Routh array. If all the elements would have been positive, you would have said that the system is stable. Okay. In the next video, we will continue with some more forms.